Here's a piece of math that should not work. Take the word king, subtract the word man, add the word woman, you get queen. Somehow you can do arithmetic on meaning itself, and the answer comes out right. This isn't a trick. It's the quiet foundation under every AI model you've ever used. Words get turned into numbers, and those numbers get arranged so that meaning becomes geometry. Let's take that apart until the king-queen equation feels obvious. Chapter 1. A word becomes coordinates. Start with a single word, cat. A computer can't reason about the letters CAT, it needs numbers. So every word gets handed a list of numbers, called a vector. Not one number, hundreds of them. A typical embedding for one word might be 300 values, or 700, sometimes a few thousand, each sitting between roughly -1 and 1. That long list is the word's address. On screen it looks like meaningless static, and on its own, it is. Think of a chess piece lifted off the board. The piece itself carries no worth. Its value lives entirely in where it stands relative to every other piece. A vector works the same way. The magic is never in any one list of numbers. It's in where that list sits, against every other word's list. But why a list of decimals at all? Before this, computers stored a word as a one-hot vector, a giant list, all zeros except a single one marking that word. Cat and kitten were as far apart as cat and concrete. Every word equally unrelated to every other. No similarity, no arithmetic, nothing but a name tag. Embeddings threw that out and packed meaning into a few hundred dense numbers instead. To see the arrangement, shrink it down. Imagine keeping just two of those numbers, an X and a Y, so every word becomes a single point on a flat map. Cat lands somewhere, dog lands close by, kitten sits right next to cat. Karen's up far across town, in a different neighborhood, with truck and road. Nobody typed in these positions. Yet already the map has structure. Things that mean similar things have drifted to similar places. Real embeddings do this in hundreds of dimensions at once. We're only flattening it to 2 so your eyes can follow. The principle is identical. A word is a location, and location carries meaning. Zoom out on that map and it isn't random dust, it's neighborhoods. All the animals huddle in one region. Countries clump together somewhere else. Colors form their own little cluster. Verbs of motion, run, walk, sprint, pool in another corner. How close two words are is literally how related they are. Measure the distance between 2 points, and you've measured how similar their meanings are. This is the single most useful fact about embeddings. Similarity became distance. A machine that cannot read now owns a ruler for meaning. Ask it what's like king, and it simply looks at the nearest points. Prince, monarch, throne. Chapter 2. Meaning is a direction. Here's the part almost everyone misses. We've been treating a word as a point, a place on the map. But the real power isn't in the points, it's in the arrows between them. Draw an arrow from the point for man to the point for woman. Now draw another from king to queen. Draw one from actor to actress, another from uncle to aunt. Look at those arrows. They all point the same way, and they're all about the same length. That shared arrow is not a coincidence. It is a concept of gender, living inside the space as a direction, not a place. A direction you can travel. Now the opening equation dissolves. King minus man plus woman equals queen is just arrow arithmetic. Subtracting man from king strips out the royalty and leaves you holding a pure direction, the male to female arrow. Add woman and you walk along that same arrow, starting from where woman sits. Where do you land? Right on top of queen. You didn't program that. Nobody wrote a rule saying queen equals king with the gender flipped. The model was never taught the word gender at all. It fell straight out of the geometry, because the same relationship, everywhere in the space, points the same way. Meaning became something you can add and subtract. And gender is only one direction. The same space holds hundreds of them stacked together, each an independent heading. There's a plural direction. The arrow from dog to dogs is the same arrow from cat to cats, from tree to trees. There's a tense direction. Walk to walked runs parallel to jumped. There's a capital of direction. The arrow from France to Paris matches Japan to Tokyo, and Egypt to Cairo. Contrative forms, verb to doer, country to currency, dozens of relationships, each a consistent path you can walk from any starting word. One space, threaded through with meaning in every direction at once. So why hundreds of dimensions instead of 2? Because meaning has far more than 2 axes. A word can be masculine or feminine, singular or plural, formal or slang, concrete or abstract, positive or negative, all at the same time. Each dimension gives the model another axis to spread words along. But here's the honest catch. These directions are not clean. There is no single column of the vector labeled gender. A concept like gender is smeared across many dimensions at once, and any one dimension is itself a blur of many concepts. The tidy arrows we drew are real. They're just diagonal lines cutting through a very high-dimensional fog. Chapter 3. How the space gets learned. Where does this beautiful arrangement actually come from? Not from a dictionary, and not from a human placing words by hand. It starts as pure chaos. On day 0, every word is thrown into the space at a completely random position. Cat is nowhere near dog. King and queen are strangers on opposite sides of the map. The whole thing is meaningless noise, a cloud of points with no structure at all. Everything we just admired has to be learned from scratch, and the only teacher the model ever gets is raw text. The lesson is brutally simple. Guess a word from the company it keeps. The model slides a window across billions of sentences and tries to predict which words show up around which. Read the sea otter floated on its back, and it learns otter belongs near sea and floated. Every wrong guess nudges the vectors, pulling words that share company a little closer, shoving unrelated ones apart. One nudge means nothing, but do it across the entire internet billions of times, and the random cloud settles, like sand finding its level. And here's the payoff nobody built in. Nobody told the model that Paris relates to France the way Tokyo relates to Japan. Nobody defined gender, or plural, or tense. The only signal was ever, predict the neighbors. Yet when the dust settles, all those clean parallel arrows are simply there. As a side effect, you optimize for a dumb little prediction game, and geometry that looks like understanding falls out the other side. But that same mechanism has a dark side. The space learns whatever the text believes, warts and all. Feed it the internet and doctor drifts toward man, nurse toward woman, whole professions quietly tilted by gender. The exact geometry that hands you king minus man plus woman also bakes in human prejudice, as clean parallel arrows nobody wanted. The embedding is a mirror, not a judge. Biased patterns in, biased directions out, which is why serious systems have to measure and correct for this. Chapter 4. Where this actually gets used. This one idea quietly runs a huge slice of the software you touch. Semantic search. Instead of matching keywords, you turn a user's question into a vector and find the nearest points to it. Search "How do I fix a flat tire?" and it surfaces a document titled "Repairing a punctured wheel." 0 shared words, but the two vectors sit right next to each other. This is the retrieval, half of retrieval augmented generation, the trick that lets a chatbot look things up in your private documents before it answers. It isn't reading in any human sense. It's geometry. Your question is a point, and the answer is whatever's closest. And it was never really about words. You can embed almost anything into a vector space, a whole sentence, an entire document, a photograph, a clip of audio, a snippet of code. Train it right and you get one shared space where a picture of a golden retriever lands right next to the text the word dog. That's how you search a photo library just by typing a description. That's how an image generator connects the phrase "a red bicycle" to the actual pixels of one. Different kinds of data all projected into the same map of meaning so that closeness still means related, even across completely different senses. Chapter 5. The link back to attention. And if you've met attention, the mechanism at the heart of every transformer, this space is the ground it stands on. Attention's whole job is deciding how much each word should listen to every other word, and it makes that call by measuring their positions right here in the map we just built. So the embedding space isn't a warm-up step you run once and forget. It's the substrate the entire model computes on, and it doesn't sit still. The classic embeddings we've drawn are static, one fixed vector per word, forever. But that breaks on a word like bank. A river bank and a savings bank can't share a single point. So attention rewrites the vector on the fly, using the sentence around it. "And the river was wide near the bank." The bank vector slides toward water and land. "And I deposited the cash at the bank." That same word slides toward money. The point isn't fixed. The space bends itself to context. Every single sentence. So here's the whole thing in one breath. Take meaning and turn it into position. Arrange the positions so that near means similar and direction means relationship. Learn the entire arrangement from nothing but which words keep company. And you end up with a space where you can search, recommend, translate across senses, and do literal arithmetic on ideas. King minus man plus woman, and out comes queen. Every model you talk to is, underneath, navigating a map exactly like this. So here's the question to sit with. If a machine can place meaning in space this well without ever being told what a single word means, what exactly is it that it does not understand? Tell me in the comments.